So, welcome back. Now, in this lecture, we shall be mainly talking about something called octal and hexadecimal number systems. But first, let us try to understand the motivation. Why do we need this? In the last lecture, if you recall, we talked about the decimal number system, which we are all familiar with. Since our childhood, we have been taught decimal numbers. So, all arithmetic that you do by hand are based on decimal number system, the things that have been taught in our schools. Binary number system is something which all computer systems are based on. That is why we also have to learn binary number system. Now, one problem with binary number system, as you can understand, is that because the weights of the digits are in powers of 2, the number of digits you require to represent a number may require many digits or bits. Take an example. So, there was an example which we took in the last lecture, a number 64. So, in decimal to represent 64 we need only 2 digits, right, but in binary we need 1 followed by 6 zeros, that means 7 bit. So, when we express a number or when you write down a number, we may need a large number of bits. So, it may be inconvenient to write so many bits. So, these octal and hexadecimal numbers are in a sense a compact way of representing binary numbers. That is one way you can look at it. Of course, they are separate number systems in their own right, but their main use is to represent binary numbers in a compact way. Okay? Let us start with this motivation. The octal number system. Octal number system, this octal means 8. Basically, this is a weighted number system with a radix of 8. So, you can say here our radix is 8, which means our digits are 0 to 7, let us say. And in this table, because I said that one of its use is to represent binary numbers in a compact. Okay, here one thing you note, that the radix that you are choosing here as 8, which is some power of 2, this is important. Because it is power of 2, so the idea is that every 3 bit binary number can be represented in octal as a single digit. Like you look at binary number 000, what is the value in decimal? 2 to the power 0, 2 to the power 1, 2 to the power 2, these will be the weights, 2 to the power 0, 2 to the power 1 and 2 to the power 2, multiply them, this is 0. So, this corresponds to 0, 001, 001, the last one is 1, it corresponds to 1, 010, second one is 2, it is 2, 011, second and third, 2 and 1, 3, 100, it is 4, 101, 4 and 1, 5, 110, 4 plus 2, 6, 111, all 3 are there, 7. So, here you see this octal digits 0 to 7, so each of them they correspond to a 3 bit binary number. This is one correspondence that we have to look at here. Now, when we talk about binary to octal conversion, this is basically following this principle. So, when you have an integer part, you scan the number from right to left. I will take examples. Given a binary number, you scan the number from the least significant position right to the most significant digit position left. And during scanning, you make groups of 3 bits, and each group of 3 bits will be replaced by the corresponding octal digit. This is the basic rule that you are following. You scan the binary number from right to left, group 3 digits each, and each group of 3 digits you replace by the corresponding octal digit. Only for the most significant part, if the number of bits left is less than 3, you can pad zeros in the beginning to make it 3. So, add leading zeros if necessary. For the fractional part you do the same, but now the scanning is from left to right. Why? Because for a fractional part you can add zeros at the end, you cannot add zeros in the beginning because the value will change. But for the integer part you can add zeros in the beginning, that is the only difference, right. So, fractional part, scan it from left to right, do the same thing, make groups of 3 bits, and for the last part you can add some trailing zeros if required. Let us take some examples. Take a binary number like this 101, 101, 000, 011. So, the number of bits are divisible by 3, there are 12 bits. So, you make groups of 3, 3, 3 starting from the least significant side 3, 3, 3, 3, 011 means 3, 000 means 0, sorry, this 101 means 5 and 101 means 5. So, it is a straightforward conversion. Now, you can see the advantage of octal. I said octal is a way to represent a binary number in a compact way. This is why I said that. There is a one-to-one correspondence. For conversion, you do not have to carry out any multiplication or division like in decimal to binary or binary to decimal. Okay. Let us take another example where there are, you can count 10 digits. So, again scan from right to left, 100 is 1, this is 4, 010 is 2, and you have a single 1 left. You add 2 zeros in the beginning, it becomes 001, which is 1. This is octal. This 8 indicates octal. So, for this case 2 leading zeros are added. Take a number means a pure fraction. So, pure fraction you scan from left to right. So, 100 is 4, 001 is 1, then you have a single 1. So, you will have to add 2 zeros, it makes 100, which is 4. And for a mixed number, both integer and fractional part, for integer part we scan from right to left, it is 1 1, add 1 0, it is 3, here 010 is 2, 111 is 7, 1, add 2 zeros, it becomes 4. So, a leading 0 is added here in the integer part and 2 trailing zeros are added in the fractional part, right. So, binary to octal is done like this. Now, octal to binary is even simpler. Just you take an octal number and each octal digit is replaced by its 3-bit binary equivalent. Like 1645, replace 1 by 001, replace 6 by 110, 4 by 100, 5 by 101. Similarly, a fractional number 2 by 010, 2 010 again, then dot 1 001, 7 111, 2 010 and so on. So, you see converting a binary number to octal or an octal number to binary is very trivial, but if you want to convert for some reason decimal to octal or octal to decimal, you can follow the same rule like in binary. Like I am giving one specific example for decimal to octal conversion. Let us take a specific example. Let us say I have a number 3762, this is a decimal number. Okay. So, I want to convert it to octal. So, what I do? I take this number, I repeatedly divide by 8, I divide by 8, 8 4 is 32, 5, 756, 0 with a remainder of 2. Divide by 8 again, 8 5 40, 7 8 64 and remainder of 6. Divide by 8 again, 8 7 56, remainder of 2. Divide again 0 with a remainder of 7. You have arrived at 0, so stop and you take it in the reverse order. 7262. So, 7262 is the equivalent representation in octal. So, conversion from decimal to octal can be done in this way, following a principle which is almost identical to that for decimal to binary. Only difference is here you are dividing by 8 instead of dividing by 2. For fractional part it is same, you this time instead of multiplying by 2 you will be multiplying by 8. Let me just take an example again. Let us say I have a decimal number at 0.356, this is decimal. I want to convert it to octal. So, what I do, 0.356 I multiply by 8. So, how much is that? 4, 24, 28 and integer part is 2. So, you remember this integer part. Now, fractional part is 848. So, you take 848 multiply by 8. So, now it becomes 6, 38, 3, 7 and 6. So, now the integer part is 6. Take 784 multiply by 8, 3, 6 like this, and this continues. So, now if you take it in the same order 265. So, this will be equivalent to 0.265 in octal, right. This is how you can convert from directly from decimal to octal or octal to decimal. Okay. Now, let us come to hexadecimal, which is one step further. Octal is 8, hexadecimal is 16. So, in the earlier case we are grouping 3 binary digits, 3 bits to form one octal digit. Now, we will be grouping 4 binary digits or bits to form a hexadecimal digit. So, hexadecimal will be even more compact in terms of number of digits. So, in case of hexadecimal number system, radix is defined to be 16. So, 16 is again a power of 2, that is why binary to hexadecimal conversions are easy, and the 16 digits are defined as follows. The first 10 are 0 to 9, last 6 are A to F, A, B, C, D, E, F. So, 0, 1, 2, 3, 4 up to 9, then A, B, C, D, E, F. This is how the 16 digits are defined in hexadecimal. Okay. So, this table shows the different hexadecimal digits 0 up to F and the corresponding binary equivalents. So, you can take any one. 0 1 1 0 means what? You multiply by the weights, it is 6 in decimal. So, it is equivalent to 6 digit 6. Similarly, you take let us say 1100, it is 8 plus 2, 12. C means 12, see 9, 10, 11, 12, 13, 14, 15. So, it represents the digits. Similarly, 1111 means 8, 4, 2, 1, 15, 15 means F. So, every 4 bit combination is equivalent to 1 binary or means equivalent to 1 hexadecimal digit. This is the basic idea. So, when you talk about binary to hexadecimal conversion, it is quite similar to octal. For the integer part, you scan it from left to right to left, sorry, binary number you scan from right to left, and instead of 3 bits, now you group 4 bits, and each group of 4 bits you replace by the corresponding hexadecimal digit. and the last one, if it is less than 4, you add leading zeros. And similarly for fractional part, you scan from left to right. So, again you make groups of 4, replace it by the hexadecimal digits and add trailing zeros if required. Take some examples here. This is a binary number. 1011 is what? 821, that means 11. 11 means the digit B. 0100 is 4. 0011 is 3. This is the hexadecimal equivalent. 16 indicates hex. Similarly, this number you scan from right to left. 0001 is 1. 1010 is A. It is 10. 10 means A. 10, add 2 zeros, 0010 is 2. For fractional numbers, scan from left to right, 1000 is 8, 010, add 1 0, 0100 which is 4. Similarly, another example here. Here you add a 0, 0101 is 5, this is 5, and 111 and a 0, it is 14, which is E. Okay. So, this binary to hexadecimal is fairly simple, almost same as binary to octal, only the size of these groups are different. Hexadecimal to binary again is very simple. You take the hexadecimal digit, replace them by their 4-bit binary equivalents. 3A5, this is 3, this is A, this is 5. 12.3D, this is 1, 2.3 and D. 1.8, 1, 8. Okay. So, in general, I just gave an example just some time back for r equal to 8. So, if you have any arbitrary radix r number and if you want to convert from decimal to radix r and vice versa, you follow a similar principle as we showed for binary. For radix r to decimal, you multiply each digit by corresponding weight and add them up. Like I am giving an example. Let us say I talk about an octal number. Let us say I have an octal number 237 and I want to find out its value. I want to convert it to decimal. So, each digit position will be they will have some weights. So, it will be 2 multiplied by 8 to the power 2 plus 3 multiplied by 8 to the power 1 plus 7 multiplied by 8 to the power 0. So, 8 square is 64, 64 into 2 is 128 plus 24 plus 7. So, it comes to 159. This will be the equivalent decimal number, right. So, radix r to decimal will follow this principle, multiply each digit by the weight, add them up. Decimal to radix will be, this will be using repeated division or repeated multiplication. For the integer part, you repeatedly divide by r and take the remainder and consider the remainder in the reverse order. I illustrated this for octal r equal to 8, and similarly for the fractional part, you multiply by r and accumulate the integer part. This also I had shown for octal. Okay. So, in this lecture we have basically looked at the octal and the hexadecimal number systems. We saw how we can convert binary to hexadecimal and octal and vice versa, because I repeatedly said binary numbers are most important to us when we are talking about designing digital circuits and computer design, because they all work on the principle of the binary number system. And also I talked about for a general radix r, how we can convert a decimal number to radix r or vice versa. These basic techniques will help you later when you want to convert any arbitrary number from one radix system to another. Thank you.